Top Secret Sci-Operative Training Mission. Reading passage: Atomic Structure and Reactivity. Mission: determine the subatomic structure of given atoms using the periodic table and how it relates to reactivity. Use the field guide periodic table as support and reference. Tips: remember to beam as you read through the passage below.
Inaya and Nikole, what brings you into the lab today?
We heard you were experimenting with copper as a new armor type and wanted to see what the hype was about.
On the way here, Nikole taught me about how the atomic structure of an atom determines the properties of each element.
Fantastic! I've been reviewing the atomic structure of copper myself to help me conduct tests on its melting point and the reactivity of its atoms. The melting point of an element increases with the number of electrons its atoms have, and reactivity is connected to the number of valence electrons an atom has.
Remind me, how can you tell if an atom is reactive?
We can use the periodic table. The atomic number shown on the table tells us the number of protons in an atom, which also identifies what element an atom is. The number of electrons will be equal to the number of protons in a neutral atom.
Oh yeah, I remember protons are the positively charged subatomic particles. Neutrons have no charge, and electrons have a negative charge.
Good memory! Do either of you remember how to find the number of neutrons in an atom?
We can determine that with the periodic table as well. The larger number in each tile on the periodic table is the atomic mass. The atomic mass is the average mass of an atom, and it is equal to the number of protons and neutrons in the atom. The number of neutrons in atoms of the same element can vary, but the proton number remains the same. To determine the number of neutrons, you round the atomic mass to the nearest whole number and subtract the atomic number. For copper, we'd calculate the number of neutrons as follows.
The image shows a whiteboard with the equation for determining the number of neutrons in an atom. Atomic mass minus atomic number equals the number of neutrons. A periodic table tile for copper is shown with an atomic number of 29, a chemical symbol C lowercase u, the element name copper, and an atomic mass of 63.546. On the right-hand side of the tile are the numbers 2, 8, 18, and 1, representing the number of electrons in each energy level for copper. Nikole has used the periodic table tile to determine the number of neutrons in copper. The atomic mass has been rounded to 64 minus the atomic number of 29 equals a total of 35 neutrons.
I have a question. I know the number on the left is copper's atomic number, but what are those numbers on the right-hand side of the element tile?
Those represent electrons in the copper atom. Copper has an atomic number of 29, so we know it has 29 protons. To be neutral, it must also have 29 electrons. If you notice, those numbers on the right side add up to 29. They represent the number of electrons in each orbital, which is a specific area around an atom where electrons can be found orbiting the nucleus.
Exactly! The numbers on the tile match the number of electrons in each orbital or energy level for copper. You can determine the number of energy levels by looking at which row it is in on the periodic table.
The image shows how an element's position in the periodic table corresponds to its energy levels. The first row of elements have 1 energy level. The second row of elements has 2 energy levels, and so on.
Oh, so elements in row 1 have 1 energy level, elements in row 2 have 2, and so on.
Copper is on the 4th row, therefore it has 4 energy levels?
Yes, the row an element is in can tell us how many energy levels its atoms contain. Do you two know how many electrons are in each orbital?
I know. The electrons will fill the orbitals in a specific pattern. The first ring closest to the nucleus of an atom can have up to 2 electrons. The second ring can have up to 8 electrons. Elements in the third row will hold 8 electrons in their third ring. Things get more complicated for the third ring when you reach the fourth row.
Copper is on the fourth row. It has a full first, second, and third orbital, and one additional electron orbiting in the fourth energy level.
Yeah, I can see the pattern now that you've explained it.
Just remember that each energy level must be full before electrons start to fill the next energy level. Now here's where reactivity comes in.
The image shows a Bohr model of a copper atom. The nucleus is labeled. The first 3 orbitals are full. The first orbital has 2 electrons. The second orbital has 8 electrons. The third orbital has 18 electrons. The fourth orbital contains 1 electron, and it is labeled as a valence electron.
Didn't you say earlier that reactivity is connected to the number of valence electrons? I know valence electrons are the outermost orbital of electrons, and they are involved in forming chemical bonds. The more reactive an element is, the more likely it is to bond with other atoms.
For the elements 1 through 18 on the periodic table, we can determine the number of valence electrons from the column in which the element is found. As shown on the periodic table below, elements in column 1 have 1 valence electron. Column 2 have 2 valence electrons. The elements in column 8 have full valence energy levels, making them very stable and unlikely to react with other atoms. After element 18, argon, the valence electron configuration gets more complicated. For example, copper can have either 1 or 2 valence electrons.
The image shows how an element's position on the periodic table corresponds to its number of valence electrons. It highlights 8 groups. Elements in the first group, or column, on the periodic table have 1 valence electron. Elements in the second group have 2 valence electrons. The transition metals are skipped over. Elements in group 3A have 3 valence electrons. The pattern continues until the last group has 8 valence electrons.
What does that tell us about the copper for our armor?
With 1 valence electron, copper is a slightly reactive metal. Think about the Statue of Liberty or an old penny. Copper reacts with oxygen, which is why it turns from shiny reddish orange to dull green. So even though copper feels sturdy and strong, based on its melting point and reactivity, it's probably not the best choice for our battle armor.
But it would make a great entry for shiniest armor in the World Armor Fashion Show.
The image shows a tarnished copper penny.
Make connections. In each box below, write a connection between a text that you just read and either your prior knowledge or something in your life. Reading comprehension questions. Atomic structure and reactivity. 1. Mr. Pauling needs you to prepare information about metals for his work on armor prototypes. Help him by completing the table about neutral atoms of the listed elements. From left to right, the headings read Elements, number of protons, number of electrons. Aluminum, silicon, beryllium. 2. Use the table below to calculate the number of neutrons in each atom listed. From left to right, the headings read Elements, rounded atomic mass, atomic number, number of neutrons. Aluminum, silicon, beryllium. 3. How many energy levels does each atom, shown in the table below, have? From left to right, the headings read Elements, what row of the periodic table is this element on? Number of energy levels. Aluminum, silicon, beryllium. 4. How many valence electrons does each atom, shown in the table below, have? From left to right, the headings read Elements. What column of the periodic table is this element in? Valence electrons. Aluminum, silicon, beryllium. Level up. 1. Of the 3 elements shown in the tables above, which element do you think would be the best choice for the next armor prototype? Consider the melting point and reactivity and how they relate to the electrons of an atom. Support your answer by citing information from the periodic table. You may need to conduct additional research using the laboratory in Sci-Ops Global Defense.